Yes. We
All
do.
right, so today we want to make sure that you got those calculations. We want to discuss the colligative properties, and if we have time, we're going to discuss making solutions. If we don't get that done today, we'll discuss it tomorrow, and then we'll try to make a solution on Thursday. And what we'll do is we'll make a solution for the laboratory that we're doing next week on Thursday and Friday. So how good you make the solution on Thursday will affect your laboratory results next week. Yay. All right. Did you have a question?
We already reviewed 5, 6, and 7.
All right. And then we didn't do 8 because it's too easy, right?
Yeah.
Okay, then. So that is what the quiz is on Friday. And I'm going to do you guys a solid, and I'm going to make that quiz available Friday and Monday. So there won't be an asynchronous assignment other than that. So yay, you're welcome for that. And then hopefully I'll be able to grade those. If you don't do it on by Monday, while I'm at school still, it may not get into the 9 weeks. Just keep that in mind, because I want to have those graded and put in the 9 weeks by probably by the time I leave on Monday, by the time I leave school on Monday. So just keep that in mind. All right, then that takes us to colligative properties. If you want more practice problems like those, it is on page 25, and I will paste the answers of these from page 25 to 26. I will post the answers to that on the Canvas probably by the end of the day today. 25, 26 is review for Friday's test or quiz. Cool. Questions on that? That'll be the 9-week quiz. Where's my pen? There we go. All right, colligative properties. Colligative properties are properties that depend on number of particles. So we understand that these particles are we know that water as a solvent is polar. We know that these particles are attracted a lot of times by that polarness. That's how we get things to dissolve into solutions. So colligative properties are basically based on the number of particles dissolved. The boiling point can be elevated. We call that boiling point elevation. So the change in temperature boiling is equal to the molality times what we call the Van Hoff factor, or the index, times the KB, or the boiling constant. Delta T means change in temperature, delta T. What's that, Olivia?
What does I stand for? I can't really see what that's.
Van Hoff factor? Is that
Okay,
better?
thank you.
It's in my ear. Van Hoff factor. It's a name like Van Hoff. Victor Van Hoff. If you don't like that, you can call it the index. it my handwriting or is the screen fuzzy? Both.
Both.
Yeah, right. And this is the molality. This is one of the reasons why we teach you to go from molarity to molality and all of that. Because this just so happens that this is based on the molality. Scientifically speaking, if you had the molarity here, it would not work. So if you want to find the change in boiling temperature, you need to know the concentration and molality. The constant for water is 0.512 degrees Celsius per molal. And the Van Hoff index factor for non-electrolytes, it is 1. Because of dissociation of ionic compounds, you actually get more moles of ions in a solution. So for non-electrolytes, for non-ionic compounds, it's 1. For every 1 mole of sodium chloride, you get 1 mole of sodium ions and 1 mole of chloride ions. Remember, it's based on the number of particles. So for 1 mole of sodium chloride, you actually get 2 particles. Sodium sulfide, there's 2 sodium ions and 1 sulfur ion for a total of 3 particles per mole. For sodium phosphate, anybody want to do it? That's a good guess, but it's wrong. Why isn't it 7?
Is it 8?
Nope. It is 4. The phosphate holds itself together. The phosphate is a polyatomic ion. So when this breaks apart, you get 3 sodiums and 1 phosphate. Yeah. How about
Did you just like count the moles? Is that what you did?
I counted the particles, 3 sodiums and 1 phosphate. 2 sodium, and because they break apart, right? They dissociate, right? How about C12H22O11? That's sugar, right? Sucrose. Nope. This is one of those student of the month questions. Nope. 2? Nope. Van Hoff factor?
Is it like 45?
Nope. Let's ask, is carbon a metal? No. So that means that this is not an ionic compound. So by default, it is 1. The Van Hoff factor for C12H22O11 is 1. The first thing has to be a metal, right? For it to be an ionic compound. You got it. That's not a metal. Whatever the first element is has to be a cation, and metals are cation, right? For it to be ionic. All right, so if 168 grams of sodium phosphate is dissolved in 2.5 kilograms of water, what is the boiling point? So we've got to change this grams to moles. 22.99 times 3 plus 4 times 16 plus 30.97.
The answer is 163.94.
So we got 168 grams per 2.50 kilograms of water. You guys cannot see that. How about now? Every 163.94 grams is 1 mole. So that will equal our molality. moles per kilogram. 168 divided by 2.50 divided by 163.94.
It's about 0.4099.
So it'll be 0.410 molal. We then need to use our formula delta T sub B equals the molality times the KB, which for water is 0.512, times the Van Hoff factor. What is the Van Hoff factor for Na3PO4? Yep, 4. 0.410 times 0.512 times 4.
The answer is about 0.8396.
0.840. So what is the boiling point then?
Where did you get that Celsius per mole?
It's the
Okay.
K sub B,
Oh, okay, thank you.
boiling constant. You're welcome. So what is the boiling point of this sodium phosphate? Nope. Nope. What is the boiling point of this solution? No. We're asking the tough questions now. No. No. The questions are tough today, huh? This is the change in boiling point. So what is the boiling point? It's boiling point elevation.
Would it be 100.840 degrees Celsius?
Very good. This is the new boiling point because water boils at 100 degrees Celsius. This is the change in the boiling point by adding this into it, right? So a lot of times you'll see like a Miss Science. They say that whenever you boil spaghetti, they say adding salt to it will raise the temperature. Will it raise it that much? You just add a pinch of salt. It's not going to raise it that much, right? This is something with a factor of 4. Something with a factor of 4, and it's not even raising it that much. But the reason you add salt to boiling water for pasta is that that's the only chance you really get to salt the pasta. So that's the thing. I mean, otherwise you have to do it with your sauce. So it changes it, but it doesn't change it that much. How many of you have a? Do you guys drive yet? Are you old enough to drive? Yeah, some people in here drive. Oh, I don't know if you do at home, but if you drive, there's something in your car that you have to add to the engine called engine coolant. That engine coolant is ethyl glycol. Ethyl glycol, when you add it to it, it raises the boiling point of the fluid, the water going through your car, so that it doesn't boil whenever it's as hot as your car is. If it boiled at then it would basically create an a gas in the workings of your engine, and if it got too hot, that gas would keep expanding until something exploded, right? So ethyl glycol, what they do is they add that so that it raises the boiling point so much that it doesn't boil. So it doesn't reach that boiling point. So I mean, that's the process that is used in common things. Now, engine coolant is also called antifreeze, right? You don't have to switch it out when oh, it's summertime. I've got to switch out my antifreeze with engine coolant. Or, oh, it's wintertime. I've got to get out the engine coolant out of my engine and put in the antifreeze. They're actually the same substance, because adding a solute to water makes the boiling point go up, but it makes the freezing point go down. We call that freezing point depression. Delta T of F equals K of F times molality times the index. Hey, pretty easy formula, right? 1.86. I'm gonna have to look this one up because I don't have it memorized. Yep, I do have it is 1.86, so I did have it memorized, but I didn't want us to work on any problems with me not being 100% certain on it. 1.86 degrees Celsius per molal. So the freezing point and boiling point are both based on the molality of the substance. Oh, look at this, ethylene glycol here. What mass of ethylene glycol must be added to 10 liters of water to produce a solution that freezes at negative 23 degrees Celsius? What is this negative 23 degrees Celsius from our formula? That is the delta T of F. Why is that directly the delta T of F? Because freezing point of water is what? Its freezing point of water is 0, right? And it's depressed. So that 23 right there, that is our delta T of F. That's the change. What is this 10 liters of water? The volume. What's the density of water? Nope. What's the density of water? Players from home. 1 gram per mole. So how much will 10 liters of water weigh? Players from home, anybody? 10,000 grams, good. And we can divide that by 1,000 and get 10 what? 10 kilograms. He's working hard on here, guys. He's running the floor with you guys. So that's 10 kilograms. Somebody give me the Van Hoff factor. Dang, he is not letting you guys have a chance. So I want you to go ahead and take about 4 minutes, and I want you to solve for the mass of this ethylene glycol with that information. Cool. I'll give you guys 4 minutes for that. Remind me to start the recording up again whenever I return in 4 minutes. Oh,
I have a question.
yeah.
Is the delta like T of F, is that absolute value?
So here's the deal. Since we it's depression, you subtract it from the freezing point, but it is a positive value, yes. You cannot have a negative molality. You cannot have a negative index, and you cannot have a negative, well, the F, K of F is not negative. Good question though, Margot, right? But none of these can be negative, so this will have to be positive.
Yeah.
Cool.
Wait, is T of F 25 or 23?
23.
Okay, on your paper it looks like
Making
25.
fun of my writing again?
No.
All right, I'm gonna be right. All right, hopefully those of you at home got it too. So let's take a look here. I want to find the mass. So I've got the delta T of F equals K of F times moles over kilograms. And then the index is just 1. So I'm going to take the delta T of F and divide both sides by K of F. And then I have delta T of F over K of F equals moles per kilogram. I know the number of kilograms, so I'm going to multiply this side by 10.0 kilograms. That will give me moles. After I get the moles, I can find the mass. So let's plug this in. He's loud, isn't he? Brr, 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 brr. Oh, that's a recording. I shouldn't make fun of people. All right, microaggressions. 10 kilograms. Delta T of F is 23. And K of F, actually, I can just do like that. K of F is 1.86. That's 1.86 degrees Celsius per mole kilogram. Kilograms will cancel out. Degrees Celsius will cancel out. I'll be left with 1 over mole, which is mole. Yay. So we get 10 times 23 divided by 1.86. We get 123.7 moles with 3 significant digits. I'll do the rounding later. The molar mass is 62.1 grams. Every 1 mole is 62.1 grams. We're going to multiply that by 62.1, 3 significant digits. I got 7,680 grams. Oops. Yeah. 2 significant digits because of the 23. Is that what you got? Home players. Hopefully you got that. That's algebraically. Oh. I used algebra there too, except for right here, right? All right. Questions there? No, no, no. All right then. So if you have this periodic table that that I had, and you know how it has on the back of it, it has this sheet of formulas. That is the T of F, K of F, and K of B are on there. These formulas are all on there. So vapor pressure, the vapor pressure of the solution is equal to X of the solvent times the normal pressure, or what we call P naught. That P naught is the vapor pressure of the pure solvent. X is the mole fraction of the solvent. Yeah. Now, what do you think? Remember, the vapor pressure is the pressure to keep the particles in. Keep the particles into liquid form. That's the pressure on top needed to keep the liquid in liquid form. If there is not a lot of pressure up here, that will cause these particles to vaporize. Do you guys remember when we did gas laws and I had that little vacuum thing and I put hot water in there? And then I put just, it wasn't boiling, but it was just hot water. And as the pressure above it, the hot water decreased, the water started boiling. So that's what we're dealing with kind of here. We know that there's moisture in the air because of water basically gaining enough energy to vaporize. We talked about how if we had a PET bowl that we put water in, it's not necessarily the PET drinking all the water. Some of that actually does evaporate. There's always the talks like in math problems and stuff like that. Like if you think about Las Vegas, they have a lot of fountains there. Well, they need to continuously fill up those fountains because of evaporation. You know, otherwise they would just get, you know, less and less water in those fountains. So we want to calculate the vapor pressure of a solution of 35.0 grams of sodium sulfate with 175 grams of water at 25 degrees Celsius. So the temperature is not a factor in this because at 25 degrees Celsius, this is the pure solvent vapor pressure. This is what we're basing all of this on. We need to find the mole fraction of the solvent. So basically that is moles of solvent over moles total of particles. That's an important word right there. So let's go ahead and find the moles of water. 175 divided by 18.02.
The answer is about 9.7114.
Good on that. Now we need to find the moles of sodium sulfate. 35 divided by 141.98.
It's about 0.2465.
Now here is the biggest, craziest shocker of all. Is this an electrolyte? So for 0.247 moles of this, for every 1 mole, how many Na2SO4 particles will I get? Or how many moles of particles will I get? 3. So if this is the number of moles of this whole, then we need to multiply this by 3 in order to get the total number of moles of particles. The water. This is the moles of water. (18.02) 175 divided by the molar mass of water. So 0.247 plus 0.247 times
Where
3
did you
plus
get
9.71.
0.247?
It's 10.451.
What's up?
Where did you get 0.247?
That is the moles of sodium sulfate. So I took 35 divided by 141.98.
Okay.
Did you get 3 because there's 2
And
and
it
A
is
and the
1
SO4 would stick together? Is that how?
You got it. It's a polyatomic ion. (9.71) divided by 10.451.
It's about 0.929.
So what that does, if we were to multiply this in half by 100, we would get the idea that mole-wise, 92.9% is water, right? This is like the amount of solvent we have compared to the whole thing. What we're going to do is, as I said, we're going to take the mole fraction of the solvent and multiply it by the standard water vapor pressure at the temperature we have. So we're going to then, this is X, and this is P naught. We want to multiply that by 23.76. 0.929 times 23.76.
The answer is about 22.073.
22.1. A torr. Since this is in torr, this is in torr. Again, remember that this pressure is a fraction of this pressure. Since we have these particles dissolved in it, the water molecules are going to be attracted to themselves and those particles a little bit more. So it's not going to require as much pressure on top to keep them from vaporizing. So it's still quite a bit. I mean, these two amounts are very close to one another, but it's not as much as it was without the particles dissolved in. Last but not least, this osmotic pressure is equal to the index times the molarity times the R constant times the temperature. Since the R constant is moles per liter, moles, what is it? Mole liters per Kelvin mole. What does that mean our temperature has to be in? Kelvin. And molarity is moles per liter. So that will cancel out. The Kelvin will cancel out with the R, and we will be left with pressure. So whichever R we use, I'm going to use atmosphere, 0.0821. So 25 degrees plus 273 is 298 Kelvin. Here's the molarity. What's the index? What's the Van Hoff factor?
3.
3, very good. So we've got pressure equals 3 times 0.50 molar times 0.0821 mole atmosphere per liter Kelvin, right? And then times the temperature, 298. So take a look again, moles per liter here. And this is what molarity is going to cancel out with. Kelvin and Kelvin will cancel out, leaving us with atmosphere. Pretty cool. 3 times 0.5 times 0.821 times 298 Kelvin.
It's 366.987.
366 atmosphere. 367 atmosphere. Yeah, it is. It is realistic. Yeah. So whenever you think about it, I mean, putting salt on a snail, there's no way that they could live through that, right? Because all that moisture, there's not enough pressure in our atmosphere to prevent, even salt water or something like that on the snail is going to be pretty bad for it, or slug. But yeah, 3 times 0.5. Make sure I got all that. Yep. That would be 1.5. Yeah, 1.5 times 200. That's already up there, right? Cool. All right then. That gives you the ability to do all of these problems, I believe. What do we want to do? Evens or odds? Neither. Let's do evens. There's your 3. Oh, yeah, that's good because it says number 2. There's your 3 problems for this evening. We'll end up doing the odds. So if you get problem hungry or whatever, by all means, go for it. Don't forget, I did have you guys check your grades, hopefully. Remember with the two formats or platforms, it's difficult sometimes for me because you have to realize I've got over 100 kids. To make sure that every single one of those is correct, it's easier for you to check. And if there is a problem, let me know, please. If you need to make up something, I'm pretty easygoing when it comes to that, so let me know on that too. Some of you guys might have had like something that you turned in, but I couldn't read the format of it. That goes down as a 0 until you return it in so I can read it. Unfortunately, whenever I grade that, I don't remember the next day who that's affecting. So you'll usually see that once it's put into the grade book. That's all I got. Have a great day. Take care of yourselves and others. Bye.
Okay, I just don't understand what R stands
Yeah.
for.
So I actually messed up. It's not going to be 367 because it should not be 0.821. It should be point what? 0.0821. So people are going to be upset about that. And then when we put that in, I think it will take it and make it 36.7, right? So that sounds a little bit better. R constant is from our gas laws. 0.0821. Remember that one?
No.
No? Would you forget all the gas laws?
Yeah, pretty much.
That was last semester, right? I mean, all those are constants. There's 0.0821 if you're in atmospheres. There's 64.3, I believe. If you're in whatchamacallit, right? So there are constant is on the back of that periodic table as well. 0.0821.
Oh, okay, that makes sense. All right, thank you.
You're welcome.
Have a good one.
Yep, take care. How you doing, Mia? Mia. She left. She was like, nope.